All right, according to YouTube, we are now live. Welcome everyone to Universe at Home. My name is Nico Adams. I am a second-year grad student going on third year who is studying a little-known topic known as clumpy galaxies as part of my PhD, which are a form of star-forming galaxies. And Aaron, do you want to introduce yourself?
Yeah. Hi. My name is Aaron West. I've talked on a previous one of these, and I do work on the aurora. I do simulations trying to predict how plasma trapped in Earth's magnetosphere moves, energizes, and leads to the beautiful illumination we can see at Earth's poles.
All right. So thank you guys all for joining us. I think we may still have a few people joining us over the next few minutes, but I'm going to jump in with a quick introduction to our topics today, and hopefully people will be able to pick it up from there. So like I said, my name is Nico Adams. This is Aaron West. We're presenting tonight on what was called online current events in astronomy. And at the beginning of the summer, we did not know what those were going to be. And boy, did we get a huge surprise about what turned out to be the biggest story in astronomy, because we did not see the first of our stories coming. The first of our stories that we'll be talking about is the comet NEOWISE, which took the world by storm and which was really came out of nowhere. In July, it just suddenly exploded onto the scene. The second topic that we'll be covering, that Aaron will be going more into detail on, is the Mars rover Perseverance, which recently launched from as a NASA probe of Mars. So we'll be talking a lot about what its mission goals are and sort of what to expect looking forward with that project. And we're excited to have you join us. So as many of you know, last month there was an extremely bright comet in the sky. This comet's official name was C2020 F3 NEOWISE. And this comet was so bright that many people were able to see it even in dense urban areas with a lot of light pollution, which is what led to the photo that you see here. This was actually taken by our own Lauren Laufman, a fellow grad student, on the roof of the University of Minnesota's own Tate Hall, which is where we have physics and astronomy classes. And it was very close to downtown Minneapolis. So the light pollution from the city basically drowns out the rest of the sky in this long exposure photo. It's very difficult to see any other objects in the sky. But the comet NEOWISE was so bright that it actually dominated other sky objects at the time. So it's all you can see in this photo. It was so remarkably bright that it was really the star of the sky when it was visible. So unfortunately, this is not going to be a video about how to observe this comet, because this comet has now passed the range where it can be observed. It is no longer as active and it is no longer as close. So from here on in, you will not be able to see it as easily, and it is not visible to the naked eye. You will need telescopes and tools. However, a lot of us heard a lot about it over the last few weeks. So this will sort of be, as I called it on this slide, a farewell tour. It'll be answering hopefully some of the questions that you may have had that linger about this comet, making sense of all of these amazing photos and amazing news stories that you've read, and focusing on three specific questions. The first is, why is it called NEOWISE? The second is, why was it so exciting, both to the public and to astronomers? And third, a short explanation of the comet's tail, which is by far its most distinctive feature. You can see it in this image if you look very closely, though it's admittedly not the best image of NEOWISE, but it is it was in a very urban area and it is still visible. So the fact that we were able to see it on such a brightly lit sky is remarkable. So question one, why is it called NEOWISE? This was one of my biggest questions going into this talk, because I had an idea, but there's this whole complicated name scheme for comets that I dug into while doing research on this talk. And it starts with the telescope that was the first to observe NEOWISE. In December 2009, NASA launched a space telescope that they called the Wide Infrared Survey Explorer, or WISE for short. This telescope is, like Hubble telescope, it is a space telescope. It observes things from outside of the Earth's atmosphere while in orbit around the Earth. And the reason that's true is that the Earth's atmosphere gets in the way of our observations and kind of blurs the light that's coming in. So we can get much better data from space. Unlike the Hubble telescope, it's taking data in a much lower frequency range. So it's taking data in the infrared, as is in the name, rather than in the visible and ultraviolet range of the frequency spectrum, as the Hubble did. As a rule, this is useful because lower temperature objects emit lower frequency radiation. So if something like the sun is emitting radiation, it's going to emit a lot in the visible and even some in the ultraviolet. As many of you might know if you got a sunburn this year or in any past year. Asteroids, comets, meteoroids cannot do that. They do not emit their own light in the visible or in the ultraviolet, but they do emit their own light in the infrared when they get above a certain temperature. So it's possible to detect them more easily in an infrared frequency band. So one of WISE's main missions was to therefore seek out small asteroids and comets that we didn't already know about, in particular objects that might be coming close to Earth, which are called near-Earth objects. So the name of this mission was shortened to just NEOWISE, the Near-Earth Object Wide Infrared Survey Explorer. So this was not the name of the comet because NEOWISE is a mission that is supposed to discover as many comets as possible. It's certainly not the only comet that NEOWISE has discovered. However, it's called Comet NEOWISE because it's by far the brightest, and there are really no competing like popular comets at the moment. So it is a comet that has a much longer name than NEOWISE, but the longer name isn't really necessary for most uses. However, it is interesting. It's cool how all these little addendums got made. It tells you a lot about comet science and about the comet itself. So I'm going to break it down. The C just means it's a non-periodic comet. What that means is that we don't expect it to come back within our lifetimes or our children's lifetimes or our children's lifetimes. We expect it to come back in about 7,000 years, as many of you have maybe heard on the news. It's on a very wide orbit that will take it very far away from the sun, and that will take a long time to complete itself and return. We give any comet that will not return within 200 years the name C. We give comets that will return within 200 years the name P. And we give comets that we're not sure about X. There was a new label that was actually added recently because we discovered our first object from outside of the solar system. So it was an interstellar object that was not in orbit around the sun at all. It was just passing before moving on to other stars. So we gave that a new letter I for interstellar. So C basically means this is the last time you will see it for human history, basically. It's going to just vanish off the part of the solar system that we live for a long time. The next part of the name is F3, after 2020, which was the year that it was discovered. That tells you when it was discovered and how many other comets were discovered around the same time. The F means it was discovered in the second half of March. The 3 means that it was the third comet found. Just looking at this comet's name, you can kind of estimate how many comets we find per year. This was the third comet found in a 2-week period. So if we make an estimate based on that frequency of finding comets, we come up with about 50 per year as like a lower bound for the number of comets that we are finding that are new. In fact, this is in the right ballpark. We find about 100 per year, and we found about 95 in 2019. So NEOWISE sort of slotted right into a huge field of comets that we were discovering around the same time. And lastly, NEOWISE is the name of the telescope, the Near-Earth Object, or not the telescope, sorry, the program, the Near-Earth Object Wide Infrared Survey Explorer, or NEOWISE. So the discovery of NEOWISE at first was not a huge deal. This is actually the first official document, as far as I can tell, that was released to announce its discovery. And this is a standard astronomical telegram. To most people, really to anyone except a cometary scientist, it doesn't look very interesting. It's a lot of text it's a lot of very monospaced text on a blank white background. And what this is telling people is that several different people observed this new comet with different instruments. And it's basically giving a list of the observations that were taken. At the time, they were very unconstrained, which means that we were observing very different things with different instruments and with different people. The reason is that the comet was not very bright at the time. So it took a while before we were able to constrain its properties and figure out more about it. And it had to get a lot closer to the Earth and a lot more active, a lot more bright for us to understand it better. So that brings us to question 2. Why was this comet so exciting for people? To understand that, I'm going to make the bold decision to show the actual light curve, the graph that astronomers have compiled on this comet. To make it a little bit simpler, because this is a very common graph for astronomers, but it's not something that is generally advertised to the general public. But it does illustrate this phenomenon really well. I'm going to add a couple of labels. The bottom red line tells you on the y-axis, we're measuring brightness, and the bottom red line measures the minimum brightness that human beings can see in a dark sky with the naked eye. So if you have a very good eye and a very dark sky, that is the dimmest thing that you can see. On the other hand, the blue line at the top measures is about the brightness of the brightest objects in the sky. There are only about 4 stars and a few planets that emit light with a higher apparent magnitude, with a higher apparent brightness to the naked eye from someone observing on Earth. So what's cool about NEOWISE, and maybe you can already see this by the trajectory of this graph over time, the x-axis, the horizontal axis, measures time in months. And at the beginning of our observations, NEOWISE was an extremely faint object. It was well below that red line. So not only could you not see this with the naked eye, it was hard for even many telescopes to make it out. As the months passed, as we got through April and May, it started to get brighter and brighter and brighter. And we realized if this thing was on the trajectory that we observed it on, it was going to pass very close to the sun. So at this point, a few popular science articles popped up and said, hey, this is something to watch out for. Maybe when it swings around the sun and comes back, it's going to be very bright and very active. We don't know for sure, but it's possible. Then there's a gap. This was the suspenseful part of NEOWISE's trajectory. And the reason is that it got too close to the sun for us to observe. We couldn't point telescopes in its vicinity without picking up mainly sunlight. So it was too polluted an area with other sources, namely the sun, to make out what was going on. So the reason that we didn't know what was going to happen after this, and the reason this was so suspenseful, is that just this year, 3 other comets have made a similar journey to NEOWISE, where they passed really close to the sun. One of them was the was an interstellar object that we were only the second one that we were to discover. Another was the comet Atlas, which came about earlier this year, and there was a third whose name I don't remember. But the point is that all 3 of them disintegrated. So there were little articles that said, hey, maybe Atlas is going to be the brightest thing in the sky soon. And before that could happen, they were vaporized by the intense sunlight that their trajectory had taken them into interception with. So we didn't know if NEOWISE was going to go the same way, but we assumed that it probably would. We didn't want to get our hopes up. So we knew that if it did survive, there was a very strong likelihood that it was going to become one of the brightest objects in the sky and a huge astronomical story. And that is exactly what happened. This is why it was such a surprise when NEOWISE emerged as this incredibly bright object that captured the public's imagination. Not only did it survive its close encounter with the sun without being disintegrated, and not only did it emerge visible to the naked eye, but it had become one of the brightest objects in the night sky. So the last comet that was this bright was a comet called Hale-Bopp in 1997. And events like this are extremely rare. The fact that it was so unexpected and arrived with so little fanfare in a lot of ways meant that it was sort of like receiving an unexpected present from the outer solar system. So that brings me to my last question. Why does NEOWISE have a tail? And is this true of all comets? Is it just NEOWISE that has such a magnificent tail? Why don't meteors and meteoroids and asteroids have tails like this? And most importantly, I thought, which is why I included it on the slide, why does it have 2 tails? A blue one that's very straight and narrow, and a curvy white one that's very diffuse. Comets are very complex, so there's actually a lot going on here to get into, and I'll do my best to summarize it quickly because I'm coming up on my time to talk about this. The idea is that as a comet is forming, it typically forms in the very far reaches of the solar system. It forms very far away from the sun. So comets are different from meteoroids and asteroids because as they're forming, they have the opportunity to form from what are called volatiles, which are things that when they're at low temperature, they're typically solid. And when they're at higher temperatures, they're typically gas when they're in space. The most famous volatile is water. If you expose water to sunlight, it will melt. We have all seen this happen. It is not an unfamiliar thing to us as human beings. But there are many others. There are 2 very important ones that we are familiar with are carbon monoxide and carbon dioxide, which are actually so cold that they're in solid form when they're very far away from the sun. When they get close to the sun, sunlight suddenly has an opportunity to melt them. And what we see is that comets start to vaporize due to sunlight as they pass about the orbit of Jupiter. When they get closer to the sun than Jupiter, all of a sudden, a lot of the things on board those comets start to just vaporize and form the tail behind them. So NEOWISE not only passed within the orbit of Jupiter, it actually passed closer to the sun than Mercury. It was about 3/4 of Mercury's average distance from the sun when it got closest at what we call perihelion, the closest approach to the sun. So by the time it came around into view from Earth, it had started to evaporate really rapidly. Sunlight had a very huge effect on it. So what we're seeing here is there is a tail of rocks and basically solid material, where each grain of solid material we just call dust. It's more complex than stuff that we normally see in space because it's made of rock. It's not individual atoms. Whereas the blue tail that you're seeing is what we call the ion tail. And those are all of the gases and volatiles that are being vaporized. So those gases and volatiles were necessary to hold the comet together. And as soon as they vaporize, the dust that made up the rest of the comet could not really hang on. So it gets blown away as well. And that's why we see two different tails. The dust is much more massive and much more complex than the gas. And so it takes a little bit longer for sunlight to accelerate it and to have as much of an effect. The gas, on the other hand, is made up of individual atoms and molecules. And that's why they accelerate away from the comet so quickly on a different path than the dust. The dust just doesn't have, sunlight just doesn't have the same effect on dust as it does the gas. The last thing I'll say before I move on to Aaron's part of the talk, because I'm going a little bit long, there's a really major question tied up in this, which is why does the ion tail glow blue? And the reason is complex, but it has to do with the fact that solar wind, charged particles from the sun, are also interacting with the gases that are being released. So radiation from the sun evaporates them and then oftentimes deassociates electrons from the molecules that are being sent away in that ion tail. And so you're left with this sort of mix of electrons and positively charged gas molecules that are missing electrons. As soon as an electron recombines with a molecule, it lets go a little bit of light that is a very specific color. And in NEOWISE's case, that color was typically blue. So other comets have had different color tails, and it really tells us a lot about the composition, the specific volatiles and gases that are being released by NEOWISE. So before I leave this entirely, I'm going to mention the one mystery that still remains, which is, well, there are many mysteries. I shouldn't say the one. One mystery that still remains is that NEOWISE gave us a very up close, very bright view of what's happening to it as it passes close to the sun. And we had the opportunity to see the details in that dust tail. And some of those details are what we call striations or bands. You can see that there are little separations between like bright areas of the tail. We're not 100% sure what causes this. We have a pretty good idea, but it's one of the most active areas of comet research right now. And NEOWISE gave us a very good opportunity to study that. So now we'll have to make sure that our models of how comets work include the behavior that we observed from NEOWISE and add it to science in that way. So that takes us to the forefront of human knowledge. I think that's a good place to leave off on NEOWISE. As is always true with these talks, please feel free to leave a question in the chat. And as you do that, we will come around to answering them as we get into the Q&A portion of the talk. And with that, I'll pass it to Aaron.
I like that as an ending. We're now at the forefront of human knowledge, and I guess that's where my talk ends. That's a strong move. That's a strong move, buddy. All right. So
I always like to end with something we don't know if possible.
Yeah. So I'll be talking about Mars 2020, the Perseverance mission. Here we can actually see the launch from Cape Canaveral back on July 30th. It's a very beautiful day and perfect situation for a rocket launch. Next one. Nico, I can't advance the slides without you.
Very sorry, I forgot how this worked.
All right, so the Mars 2020 mission launched on July 30th of this year, and it will reach Mars, its destination, on February 18th, 2021. It's been going for a little bit right now, but it has a very long journey ahead of it. NASA's goals for the Mars 2020 mission can be roughly combined into three bullet points. Number one, the thing that we've been really concerned about for a very long time, searching for signs of life and habitability on Mars. A second one is a more recent thrust of research, ground core sampling, caching, and future analysis research. That's something I'll go into in a bit more detail later. And finally, test technologies for future human Mars missions. This is a really foundational step that we haven't seen on earlier missions. Some of the more recent missions to Mars actually have determined that the radiation load on the surface of Mars makes long-term human inhabitation of Mars difficult. So ideas have shifted more towards underground human habitation on Mars. But this is another aspect of future human manned missions. Next one. So where is Perseverance landing? Perseverance will land at Jezero Crater, which is this very beautiful combo image. This is a combination of ground spectrometry and satellite imagery. So you can see the depth, that's all the shadows. You can see kind of like over to the left-hand side here, where it becomes black and white. There's no spectrometry data being overlaid on top of it, but all of the colors show the different minerals we expect to find when we actually get to take in situ measurements on that exact portion of ground. And you can see from the shape of this region, this was some kind of ancient lake delta system. We have rivers pouring out and filling in a region. And this is something that geologists and planetary scientists are really interested in, because it has a high potential to preserve signatures of past life, either in terms of soil structure or in terms of organic molecules that would have to have been processed by some form of microbial life in order to be left behind. The big problem, though, is this looks very rocky, and that means a very tough landing for the rover. But NASA has a way around it. And that's going to be the dynamic landing system. So Perseverance will be lowered to Mars' surface in what is called a sky crane maneuver. This was used by Curiosity back in 2012 because, just like Perseverance, it is much too heavy for a traditional balloon landing, which is actually something we'll talk about at the very end for our at-home project. Actually, for a sense of scale, Perseverance in this image is roughly the size of an SUV. So pretty big. And if you look above it, you have all of these wires connecting Perseverance to this shell that it detaches from. And that is the second form of the dynamic landing. The sky crane allows Perseverance to impact the ground much slower than it would otherwise. But also there are cameras on the shell that allows it to notice, oh, I'm above a slant, or I'm above like a rocky crag, and moves from one side to another before lowering even farther. And that's automated. That's not controlled by anyone back on Earth, because the latency between Mars and Earth is roughly 20 minutes. It'd be very hard to pilot something with that kind of latency. So this is a big old picture of the primary instruments on Perseverance. And these instruments all play one or more roles in the primary mission of searching for signs of life on Mars. So the first one I'm going to talk about is Pixel. Pixel over here is on this extendable arm, which is almost as long as I am. And that is an X-ray spectrometry tool. This is used for rock and soil analysis. where it detects different types of what could be organics, or just in general, different types of crystallography in the ground that play into did this form from deposition? Did this form in a more tumultuous, as in like mixed or churning river situation? I'm not a geologist. I'm going off of what I've learned from my geologist friends in planetary sciences. After Pixel, which is a very cute name, we have RIMFAX, which is a ground radar system. Now, ground radar is used to probe underground features like ice and water, but also it can detect changes in the packing and density of ground, which can lead to other information about how different types of either riverbed or lake bed or something else were laid down and eroded over time. And after that, we have Sherlock, another excellent name. There's a bunch of creativity going into these. This is a different section of the electromagnetic spectrum. This is a UV laser that is specifically tuned to look for organic compounds. And it's actually paired with Watson, because Sherlock shouldn't go anywhere without Watson, which is a visual camera that will have a visual comparison to back up the spectrometry data. And finally, this component over here is a little bit harder to see because it's integrated into the body of Perseverance, is what's called MOXIE, a solid state atmosphere electrolysis experiment. Wait a minute. What is that supposed to be? So I actually have a diagram to go over what MOXIE really is, because this might come as a bit of a confusion point for people who haven't done chemistry or haven't seen chemistry in a long time. So MOXIE's entire purpose on the rover is towards that third goal I talked about earlier. That's testing technology for future manned Mars missions. If you want to travel all the way to Mars and travel back, you need rocket fuel, and you need a lot of it. One of the problems, though, is that rocket fuel is heavy, and ideally you want to use all of it before you get to your destination, so you're not using any extra on top of that. It's not a very forgiving equation. But there is another option. MOXIE is intending to take the Mars atmosphere, which is primarily carbon dioxide, and use what's called solid state electrolysis to break apart the two oxygens and carbon from two CO2 molecules into carbon monoxide, and remain with molecular oxygen. And that molecular oxygen can then be stored for rocket fuel. If that experiment works, then there's a secondary experiment that MOXIE is prepared to make, which will try and prepare the methane that would be used for the other component of that rocket fuel mixing agent. The next section is about the core sampling. So this is a NASA doesn't send these rovers off to Mars and just assumes they're going to be there. NASA sends them and says, all right, so this is if things go poorly, this is if things go well, this is if things go really well. This is one of those situations where they've designed an experiment that works for that entire prediction. So core sample caching is where you take a little drill and to drill into the rock, ground, etc., soil if it's compacted, and you take out basically a little pencil-sized tube and put that inside another sealed aluminum tube. Now, once that's sealed, Perseverance stores it and labels it inside a larger cache, and these caches are intended to be stored on the surface of Mars for a future mission to come and pick up and take all the way back to Earth. So this has been a long time coming in preparing this, but as we can see on the depot caching strategy image down here, the assumption is Perseverance will go between 2 primary locations, and then if Perseverance is still working all right after its primary mission is complete, its extended mission is to go to 2 additional locations and take more cores along the way. And finally, there's the additional experiment, which is the drone flight experiment. Ingenuity, as named by a very enterprising student in the US school system, is an autonomous helicopter drone. It's got 2 counter-rotating blades that will be detached from underneath the rover to test the viability of future drone missions. This has been a long time coming for planetary missions, because rovers can only do so much, and they are hardy but still somewhat fragile, and they can't really handle cliffs at all. But drones would be able to give us some vertical lift and the ability to scan larger sections of Mars's surface in higher detail. So Ingenuity is, just like the MOXIE experiment, a footstep towards something bigger in the future. But I find something very interesting. Because Mars's atmosphere is so weak and sparse, Ingenuity, in order to actually attain any sort of lift, only weighs 4 pounds with a 4-foot rotor span. That's a 4-foot diameter. So it's pretty big and very, very light, because anything heavier and it probably won't be able to generate any lift whatsoever. And I want to leave you with a little bit of a glance towards the future and some interesting hope. These are just 3 upcoming space missions out of a very, very large selection of space missions. Euclid is one in 2022 that is focused on using infrared, using an infrared telescope to look for origins of dark matter and dark energy in our universe. Program Artemis in 2024 is NASA's, I think, very aggressive plan to take a manned mission back to the moon and put a human on the moon for more experiments. And with the potential, you can see in this image, Mars right behind it, establishing the moon as a footstep between Earth and future manned Mars missions. And finally, by 2030 sometime, it's not finished quite yet, the Europa Clipper is a mission that we're sending all the way out to one of the moons of Jupiter, Europa, which is probably our second, or probably our best bet of finding life on another astronomical body, because Europa is a moon that is covered in ice with, at least as far as some measurements say, liquid water underneath. We haven't been able to verify that yet, so the Europa Clipper will be a high-resolution mission to be able to use some of those same radar techniques to probe underneath the surface and see what exactly awaits us there. So that's what I've talked about. That's the Perseverance mission. Those are some future NASA missions, and so I brought up before the dynamic sky crane maneuver that will allow Perseverance to touch the surface of Mars. But that's not the traditional way that NASA has delivered rovers to Mars. The traditional way is this very cute and idiosyncratic selection of balloons tied around the lander. And this is the project we have for today's presentation. which
Before we do that, we have a few minutes to take some questions from the audience.
Yeah.
So
I got
if you have
ahead of
questions
myself.
about anything that we've talked about or anything about space in general, feel free to ask. So I'm going to jump in actually with a few more comments. First, that we will probably do the egg drop experiment by about 8:45 or a little bit after, depending on how many questions there are. Second, that this is actually our last event of this kind of the summer. Universe at Home, as some of you may know if you've been tuning in for a while, is a replacement program for our usual in-person outreach events. We are graduate students at the University of Minnesota. We often do things with telescopes and state parks called Universe in the Park. Because of the pandemic, we are unable to do that. So this is our replacement program. And I think so far we have all had a huge amount of fun doing it. It has been really satisfying to see some of your comments about how it's gone. And if you are a regular tuner in, or if this is a tune in person, member of our audience, and or if you are just tuning in for the first time, thank you so much for joining us. And this has been a real adventure for us as well. So thank you. And with that, I think we should move on to some audience questions. So
Okay.
I can start us off with the very top question. Do asteroids or comets emit in the radio band? Asked by Mr. Fizzer. And I'm going to throw this one to you, Aaron, actually, because I am not off the top of I have an answer, but I'm not off the top of my head sure.
I am not immediately sure either. Again, I'm more focused towards Earth's magnetosphere, and asteroids are a little bit outside my purview.
That makes sense.
Throw out your answer, and I'll see if I disagree with it.
Yes, everything emits in the radio. The reason I say that is that everything emits light over what is known as the electromagnetic spectrum. And depending on an object's temperature, it is more or less likely at any time to emit light of particular frequencies. As objects get hotter, they are more and more likely to emit a photon of higher frequency. But they typically emit most of their light and most of the energy of their light at a specific frequency, and that's determined by their temperature. So the reason we don't use radio to study things like meteoroids and asteroids is that they're typically far too hot to have their energy concentrated in the radio. Even the coldest stuff in the universe, the microwave background radiation, is named after microwave radiation. It really only emits, it concentrates most of its radiation in the microwave. So radio is used for some very exotic events and very fast-moving objects. But for stuff that's in our own solar system, we really don't use anything lower frequency than infrared. That's like the best tracer of objects that we have. Do you have anything to add?
Nothing to add other than because emission isn't just flat for everything along the band. There is always a chance of something else emitting more strongly in the radio next to it, and overwhelming whatever signal you would get from some object like that. So while things might emit in the radio band, it's I think more likely that stronger radio emitters will swamp and make it impossible to measure everything, at least in our solar system.
All right, so I'm going to take the next question. Jim Pogue asks, why does the vapor form a tail having to do with the comet? And I think this got put in the chat before I answered the question a little bit in one of our slides, but just to reiterate, if you're curious, comets are unique because they're made up of both rocks and the same stuff as meteoroids and asteroids, but also volatiles. And volatiles are named that because as they get closer to the sun, they melt and they evaporate. So the vapor forms a tail. I guess that doesn't really answer the question of why it forms a tail. And the reason it specifically forms a tail, instead of just forming like a cloud around the comet, is that as sunlight evaporates it, one side of the gas actually has more energy all of a sudden than the other side. This side gets hot, this side is cold. And so what I'm really trying to describe is something that in physics we call radiation pressure. When the sun is shining on something, it actually imparts pressure. It actually imparts a push. And as soon as that happens, it can actually power stuff to move, sometimes very dramatically and very rapidly. It's a really important force in space, a little bit less on Earth because we have much more powerful pushing forces to deal with on Earth. But that's why it forms a tail. One of the cool things that I didn't get to talk about, and that I will now take an excuse to talk about, is that if you look at where the sun is and you look at the direction of the comet's tail, the tail always points directly away from the sun. And the reason is that the sun is pushing all of that material away from the comet. And you can see that very clearly by how the tail, but just by looking at the direction that the tail points. So you know that the sun is the culprit.
There's a secondary component to that direction as well. The sun is consistently putting out, I believe, Nico, you brought this up, a solar wind, which is an outflow of plasma from the surface of the sun throughout the rest of the solar system. And that solar wind carries with it some mass and magnetic fields that can sweep up charged particles and even neutrals with it and continue carrying them outwards. That's actually a component of why the two tails coming off of Comet look different, because one is more charged than the other, and therefore obeys the magnetic fields in that solar wind more strongly.
Okay, I think that was a great answer. I think I'm going to challenge us to do a lightning round to try and get through some of these questions so that we can get to the
right.
egg drop experiment, because I promised around 8:45 and it's getting very close. So the next question is from Raja. How has COVID-19 affected research in space? And I think we can safely say quite a bit.
Yep, just like everybody else.
And one of the ways that has happened is that one of our own, in a panel that we had a few weeks ago, mentioned that Bob Gers, the professor, one of the professors who uses a telescope who would be studying the comet, was unable to reach it because his facility was not able to open safely. So this rare opportunity to study this comet was by that one telescope lost. We still do have scientists studying it though. And I'll pass the next one to you, I think. John asks, what is the best theory for the formation of the bands in NEOWISE's tail?
Okay, so I have my own pet theories about this, but I'll go with the general accepted idea because it's a lightning round. There is what's called a current sheet coming out from the sun. You know, part of this is when you have a magnetic field needs to loop. It can't just have a single direction to it. It needs to close. And one consequence of that is there's basically like a skirt coming out from the sun that has ripples and et cetera in it, along which there are broad currents like you would find in home electronics, and that current charges the dust in the dust part of the tail and makes sections of the tail obey that magnetic ordering, what's called I think a synchrotron pressure. And my own personal theories you can ask me about if we have time at the very end.
We can always stay on a little bit later to answer questions. I think the important part is just to get through as many as possible before the official end of the event, which is at 9 p.m.
So next up is, how is gravity at Mars? Is it the same level as Earth? No, Mars has gravity that is, I think,
38% is the number.
38. I was going to say 40%. That's pretty close. I think that came up. I think that came up because I talked about the mass of Perseverance landing. So part of that is it's still coming off of a rocket and it's still falling into a planet. It needs to be braked somehow, and the more massive it is, its terminal velocity is going to change based on mass and structure. So even though Mars has a lower gravity than Earth, Perseverance still needs this sky crane maneuver to prevent being junked upon landing on Mars.
All right, we have 2 questions remaining, and let's see if we can get through these quickly so that we can do the egg drop. Yeah. So the first is, and I don't have a good answer to this, unfortunately, from Kurt. how do they sterilize, remove all life from the rover before it's sent to Mars?
So this is a multi-step process, and it's thought about by NASA from the beginning. Many parts of the rover are built in clean rooms to prevent any sort of biological material from getting in. Even so, they put the rover into an oven and heat it up super, super high. Various electronics are isolated from this heat, hence the clean room. But the general answer is they burn it.
So the same way we sanitize our food, which is interesting. I did not know that.
I mean, it's the same way I sanitize my food, but I typically call that cooking.
So last question is from Ben. Will samples be taken for the Europa mission? And what challenges are there in doing so? And lastly, what is the temperature of Europa?
Oh, those are some really good questions. Again, I'm entering the planetary science world, so I don't have all of the Europa information off the top of my head. I do know that they want to take samples from the Europa mission, but the problem is a return journey from Europa would be prohibitively long. The better bet, and missions are still in the process of having components added to them and taken away. The better bet would be to have a onboard laboratory that we could do tests on and then return the data to Earth to analyze. Maybe in the future that'll change, but for right now, I think the hope is when we can actually get a lander on Europa, we'd have a satellite already around Europa, and we can use that to communicate back and forth and have the lander take coring samples, the same as on Mars, do sounding, do all of the in situ measurements that we would hope to be able to do if we were there in person, but we'll have to settle for doing by proxy. And
all right, that was a great set of answers.
Europe is extremely cold. It's a massive moon entirely of ice. Maybe entirely of ice. We're still not sure.
I think I'm going to cut you off there because I think it was a fantastic set of answers that I am less familiar with. So I'm very glad that you were on this event. So I'm going to transfer to our last event of the night. And that will be the NASA egg drop experiment, which I'm going to transfer to as dramatically as possible. So the nature of this experiment is that, as you saw, NASA has a very specific way of delivering most of its payloads to Mars recently. And that involves basically inflating a giant balloon around the payload and attaching a parachute to the top. NASA spent millions of dollars on this, and getting it to Mars was a whole other matter entirely. Just for fun, they also published instructions for how to do it at home on your own. So we are actually using a one-page instruction sheet using materials as simple as cardboard from a cereal box, balloons, and a trash bag and some string. So we actually did this yesterday, me and my associate Lauren, who is a fellow PhD student. And we managed to successfully have the egg survive the drop. But just to show you what we were working with here, this is the lander as it exists so far. It's 2 balloons, which I will tape a few more on as I'm talking, and a little cardboard lander made out of a Cinnamon Toast Crunch box, because that was what I had around in my kitchen. So that's this little eye, is the logo for Cinnamon Toast Crunch. So what I'm going to do is, on camera, I'm going to take our real egg. It is not hard-boiled. This is a regular egg. I've drawn a smiley face to distinguish it from, to just develop some camaraderie with the egg to make it as memorable as possible. And I have inserted it into our lander. Aaron, can you see that?
Hold it up a little bit higher. Oh, rotate. There you go. I can see it just in there. Okay,
so I'm going to have to do a little bit of this off screen, unfortunately. So you'll have to trust me that I really am putting this together in front of your eyes. Now, the way that this works is you essentially cut out a triangular enclosure, a tetrahedral enclosure from a cereal box. You punch a few holes in the top, and you loop a string through those holes. And what that does is it gives you something to tie the parachute to, while also making a secure, sort of openable enclosure that you just saw for the egg to sit in as it does the drop. We will be dropping to a second story window. And in a few moments, after I finish taping on the last few components, Lauren will come in. We will do a mass exchange of the rover just for pandemic safety. And then we will drop it from what is actually my parents' bedroom, because I am now sitting for my parents while I am doing this video. So I should be ready in a few more moments if you'll bear with me. This is the part where we did as much preparation as we possibly could. This is the part in a cooking show where they would have a cake ready in advance. Unfortunately, we wanted that moment where we showed people what the egg looked like beforehand, and we wanted to make sure that people knew that it was the real egg. And
I for one, always think to, when I do a cooking show, to demonstrate that I'm actually using eggs and not ping pong balls.
So the last thing I'll say is that we very much encourage you to do this at home, especially if you are in a household that is unable to safely return to school in person. This is a very cool experiment that you can do on your own with very easy to attain household materials. So I believe the caption to this activity that I put on the website was, do try this at home, because it is extremely fun. We had a lot of fun putting it together. And in our test drop yesterday, it did survive. So we'll see how it goes today. All right, with that, I will mask up and I will summon Lauren to do the exchange.
Start when you're ready to go.
So in order to watch this, I don't have a very high quality webcam, but I will do the best that I can by repositioning my computer to look out of my porch window. And I will use some lights inside. And also activate the flood lamp that I prepared outside. All right, not yet. Aaron, can you see, can you reasonably see the area outside?
I think I can, yeah.
All right, I think we are just about ready. So we will have to recover the lander and show the results separately, but we'll hopefully at least be able to see part of the drop. So I'm going to give Lauren the signal. All right, we're ready. All right, how much of that were you able to see?
Pretty much everything.
Excellent, I will go recover it, and then we will see how we did.
And I'll actually point out that this is an experiment that you can do a lot of other things with. You can play around with what the lander is actually built out of. You can use different size balloons to see if that changes the impact. You can try it from different heights. I actually, at least back in my undergraduate days, set it up on a water rocket and launched it as high as it could go to see if it would be able to withstand unfurling the parachute and landing from, I think it was maybe 4 stories high. And there's a bunch of different parameters you can play around with for this, and there are no wrong ways to go about experimenting with making your own lander.
All right, so I have the recovered lander right here, and I'm going to demask so I can more easily talk about it. Let me see what the easiest way is to unfurl it. The egg looks pretty much intact from what I can see, if you can hear me over these balloons. All right, so the good news is, as you can see, the egg is 100% intact. It survived the second story drop with absolutely no problem. And if you saw, I'm not sure how well this got captured, but it actually hit our outdoor fire pit, which is a very tall structure. It's very uneven ground, is what I'm trying to say. So we just had our egg survive an unusually rocky landing onto a very hard surface, which is my outdoor patio. So I would call that a very rousing success. You can investigate the egg fully for yourself if you would like, and you can see that it is crack-free. So unfortunately, that is the tallest window that I personally have easy access to at the moment. So I very much encourage you to try throwing it from somewhere higher. We just barely had enough room to have the parachute inflate and slow its drop. But if you have a larger area to let it fall, I'd highly recommend it. I will also add the description of instructions for how to put this together to the what do you call it? The description of this video. I think that's the best place for it.
Or the doobly-doo, depending on how much YouTube you watch.
Sorry, the what?
Never mind. It's a slang term.
All right, I am not familiar with it, so I will just have to trust you. But I think, yeah, I think that is the best way to share it with as many people as possible. If you are curious as to how we put this together or just want some tips and tricks, feel free to email us at, I will add my email as well to the description of the video. So with that, I think that's a good place to wrap up. If anyone else has any questions.
I have one thing I think people would really enjoy doing. It's the end of summer. Go out and see if there are water balloons you can use anywhere. So you can use water balloons instead of larger balloons and see if that changes the impact at all. You also get a lot of them in a very small package. And, who knows, maybe actually partially filling the water balloons will change it. Maybe, filling them with just air, maybe filling them with a bit of sand. There are a bunch of different things you can play around with.
That's an interesting point. I feel partially filling them would make it heavier, but could potentially add more padding depending on how the water responds. Yeah, so I'd recommend people follow the instructions if you are feeling uninspired or just need some guidance on your first time. I'd also highly recommend that people experiment, see what works, see what doesn't. Eggs are not very expensive and are very delicate. So they're an excellent way to just quickly experiment with something at home. Especially if you're at home from school, unable to get in and do experiments in your science class in person. Personally, I had a lot more fun with this than I did with a lot of my sort of middle and high school science class experiments. So I would do this again, and I would recommend others do as well. All right.
Well, thank you for having me on, for letting me talk about this stuff I really love. And thank you to to everybody who tuned in. And helped let us know that this is something that we can start doing more of in the future.
Yeah, thank you all again. And with that, we will sign up for the summer. We will hopefully be able to let you all know if we do more events like this in the fall. That is currently up in the air, but we're hoping for the best. So have a great night and have a great rest of your summer.